one is the projection onto this thing here. Right? So, and this one is projection onto the coordinate system. That's its coordinate. Now, what do we want? We're interested to find is this V vector. V vector, the V vector is equal to what? P vector, this vector, P1 minus P0, right? Okay, so you know how to do the difference between the two. So what is the difference? You know, I take the coordinates, you maintain the ijk of the unit vector of the coordinate system, you get that V. And you get that V, you can take the modules, V, right? And then V over V, you get you unit vector V, normalize that. Okay? So that one will give you the unit vector, essentially the magnitude becomes 1, and then the orientation with this respect to this axis. So this thing, if you look at this one, the V becomes here. If I shifted this V down here, this is my V. So now this one, the angle with this axis, and with this axis, we call it direction cosine, the angle that forms. So direction cosine tells you the orientation of this axis with respect to the major axis. Okay. That's one way. So you need to figure out this, the P2, oh, he is P1, P2, and then the U. Okay, so let's read. Here three entities specified in this rotation. There's a fixed point, so P0, okay, P0 is the fixed point. What is the problem? Assume that's the center of the Q. Okay, so this is the object. I'm going to use this one around. Now this entity will allow a frame, then we have just specify rotating. Define a line during some frame. So the vector about which we wish to rotate a Q can be specified in various ways. I'm going to use V. So here's we define a vector of U, P2, P1. Okay. And then what he just did was, once you have the U, you divide by its modules or the magnitude, and then you get the univector components. And it happens that the component of this univector is the same as a cosine, direction cosine. That's the nice thing. So we need to do this first one. Coming back to read this one. In the same direction, the simplified subsequence. We say that V is the V is the result of the normalizing that vector. So we already have the univector so far. We have already seen that moving the fixed point to the origin is very useful. Because the first translation is translation back to minus P0, right? So if we see our case here, if we use this as P0, so this is 0. So if you want to move this P0, we want to use our P0. We call this one P0. So we have to move this thing back to the origin. So by how much? By this position, right? And which is the position vector. We know exactly how much to move because we know the components to go backwards. Okay. So essentially it's translating back to T minus V0. So first is translation, and then the last one when we come back, we shift back to the original place we translate back by T0. So it says that after initial translation, the required rotation problem is shown in the next figure. So we are taking this point and rotating around this axis. The axis now is already putting back to the he's using the object, the point, that's what we want to rotate. So actually, it's a little, so he's using the P0, well, let's read, let's keep reading and see whether, if you have any questions, stop me. So the problem is more difficult if we do not know what angle to use for it. The problem is more difficult because we don't know the angles to use for each rotation. So our strategy is to carry out two rotations to align the axis of this vector with the z axis. So you can rotate aligned with any major axis. The sequence will be different. Yes?
So you basically want the line in every single plane. You want the XY plane, YZ plane, and then XZ plane.
I need to, currently it's not on any one of these planes.
Right.
First one is to rotate anything such that we're going to stick with one plane.
Right.
Okay? But how do you rotate this? You have to pick one axis that we know how to do that.
So so we pick the center of the cube or the zero?
No,
zero?
we're not doing the center cube yet. I'm just defining my rotation axis.
Okay.
So remember, this is after I have this my rotation. This is my point. Okay, I'm gonna rotate around this circle here.
Okay.
And this is my rotation axis. Okay, and this is my cube, whatever center of my cube. Okay, and then after I rotate around, this one's supposed to be here, right? Somewhere here.
Right.
Okay? The problem is I cannot rotate around here because I have no knowledge about this axis. I only know rotate about one of the major axes. So therefore it's what? I take all this pure move. Of course, when I move this one, the whole thing moves with it. But I'm moving the axis.
Okay.
Okay. And once my axis down here, my object is down there too. And then once I align it, my object is also aligned because here, that's the beauty of the thing, right? The whole thing is, if you apply the same transform, they will do the same changes. Good. Keep asking questions because I don't know whether you're visualizing this or not. You have to be able to kind of grasp with the geometry. So our strategy is to carry out two rotations to align. And as I said, I'll do first rotation about x's and then by y, and then once to align with z. So here's the sequence. Rotate accounts x by this theta x angle. Rotate by y by theta y, and then rotate by this theta. That's the one I want to move. And this is the angle that I want to rotate from here to here. Right? And this is the actual angle I want to change. This is theta. Until then, I need to take this one down to this axis, one of the axes. And then I go back, reverse back process. Now, so the question here is what, I know the theta is given, but what is the theta x? What's the theta y? So here's how to determine these two unknowns. But we have some information because we can move the vectors alone, and then once we put the vector anchor onto the origin, and then if the vector is a univector, that projection becomes the angle. That's the thing. So we know the size, the magnitude, the univector size is 1. All these components squared, you get 1. Right? That's the property we want to use. Okay, so that's the derivation so far. Here comes, follow the figures. This figure is probably very important for you to follow if you can visualize properly. this line's now moving here, and its component is alpha x, alpha y, alpha z, but the angle with these major axes is called phi x, phi y, phi z, right? And this is called the direction angle. It's called the direction angles because that's a unit vector, and this is equivalent to be the 1 over the angle cosine of the angle. Therefore, is equal to the cosine of the angle. The projection of that unit vector onto the plane, right, by the angle is a cosine component onto that. So it's cosine. So we know, so the angle itself is cosine of that angle is equal to the component of that unit vector. Aha. So, but we know alpha x, alpha y, alpha z. So we know the angle, right? That's helpful because since we need to know about the three angles, and two of them are independent and one is dependent. So how do we find it? So this is a key figure. So you take this, so you take this vector, right? The previous vector here. And then flip. We're rotating around x now. Now, which one? So if I have this axis here, now which way should I rotate? This way or that way? How do I know which way? Remember, rotate it by certain angle alpha along certain axis. And this is alpha to be positive. We're rotating counterclockwise if you're looking away from the axis, going back, looking back at the origin, right? Okay, so here's, if you use that angle first, we just flip positive angle, because the angle, the value that we get is positive. So this thing will go from here, to here, until you lay this one into this particular plane. X, actually, this is right-handed. I should draw the z-axis here. If I call this y, so this is minus z, this is z. Okay. So this becomes on this. Did you follow me? This one. This is a critical one. Yes. That's the only trick that you have to follow. So what we did was rotating around x this way. Follow the arrow. And this will be on this plane, xz plane now. Okay? But when you put this one, this is one still because this is the radius. But we don't know exactly the angle that rotated. When this angle, this rotation angle projected onto this one is not very clear. But here it says the theta x and theta y later when we use this angle. Let's see this 56 figure 4.56. Shows the effect of desired rotation point alpha x alpha y is to rotate the line segment onto y equals 0. Therefore, we are in the xz plane. We see the line segment. So here's this one projected. Here's you projected here, and then when you put it here, now the projection of this line is this way, right? It's projected on here. So we know this line D, and then this is actually the actual angle that we need to rotate. So this is not very clear because it's kind of a rotating space. But on one plane, this angle becomes very clear. So what is this projection, D? Well, you actually can find because we know the projection of that. This is this component, that component. So D is component. So D is the square plus square of the Z, right? So and then you take the square root. So we know D. cosine thing, so we actually don't need to figure out this angle because we only need to know the cosine and sine. And the cosine of this angle is what? Alpha over d, right? Cosine actually, the z. Alpha z over d, cosine. Sine is this component. It's alpha y minus over d. Okay? So, through the alpha x, y, z, and finding the d, and d we can combine, we can compute. So we know d, we know all the three components. Now we know the rotation angle for this particular step. Now, once we have on this plane, x, z plane, now we need to rotate around y, right? So if we look at that one, going around this way, positive should be counterclockwise, it's going to be that way. But you notice that's we're going this way, so this should be the negative part. So here's the angle is clockwise about y, therefore, so we have to be careful about the sign of the terms. And we know this will be the one, and then this will be, why is this d? We compute ry, this angle is clockwise, so cosine, and the y is the opposite side, so we actually change the sign too. Right, remember the rotation y? What is the rotation angle around y? Rotation y by certain angle, say alpha, theta. What is the transformation, which is? Zero, 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 1, 0, 0, 0, 1, and then y is 1. Now across diagonal is like cosine of theta, cosine of theta, minus sine theta, sine of theta, right? Well, sine of theta is minus, so this becomes minus. Okay? We're rotating negative. Therefore, we get the minus here. Okay? And this sign of things is actually this component's alpha x. So we're looking at this relationship. Because this is the alpha x. Sine is alpha x. So now d, why is the cosine is equal to d? Cosine is the projection. When we flip this down, this is actually, I can't see. Okay. So when this thing flipped down, the d will be aligned with this one. But this is actually the actual length of that axis component. Make sense? So now we got this two, even though we didn't know about the theta x and theta y, but we can derive that by looking this two movements in order to generate this work. Okay, now having this one, we essentially solved the problem, right? Because we need to know about the angles rotating Rx, Ry, and then going backward, the inverse is very easy to find. We just flip the signs in here. And also the translation is the same thing. We just flip this one. And this is the angle that's we're looking at. So now you can take all these 5 angles and then multiply together into a big matrix. And that's the rotation matrix. However, has to know the alpha x, alpha y, alpha z, which is the orientation of that rotation axis. Make sense? So that you have to compute. Now how to compute? As we said, you have to take the vectors, 2 points, find the vector, and normalize to the unit vector, and be able to figure out this one. This is what we do. In the book, instead of the translating the x's, assume it's already translating, so you have a rx by this angle by, so how do I specify my orientation? You have to read the problem carefully, right? So if you want to rotate the objects by 45 degrees, so here's the rotation line passing through the origin, and then the points 1, 2, 3, and that's the position vector of the point that gives you this rotation axis. If that point is 1, 2, 3, we leave the fixed point at origin, the first point, the final point along the line. Therefore, we need to do the alpha x, alpha y from this vector, and this is converted to homogeneous. Take about this point, we rotate it here, we get our x-axis by this basic components. Matrix theory. Here's a simplifying things. Once you put all this, you multiply, now you get make sense? Okay. Are you follow the derivation? Yes. So on the test, I'm going to ask you this question. Let's define a problem. And I said, how do I define a problem? I was looking for, you did the framework. So for this room, you know, this way, our ruins is very weird. And then we have a door, closet door here. It's like, which way? Left. So it opens up. Here's this one opens up and we have that door. Two doors. There's one okay, if you look at the door, okay? So I want you to say, hey, how do you open a door? What kind of transformation you want to the modeling of all these things. Now you might say, hey, show me the transformation in order to show my door, assuming on the original door you have used here. I want to find this point. And after you rotate it, where is that point? So essentially this point has to go rotating based on the inch, right? Now in this particular case, the axis is along one of the axis. Maybe it's easier. But if I give you one of the coordinate system which is not one of the major axis, then you have to figure out how to align it. Okay? You also have to figure out which one to what? To move. So you have a sequence of operations. So here's going through the, let's say the handle, and then I'll open the door. That's one typical problem I can ask you. Makes sense? If you go home, this will be the pre-test. Figure out the transformation, and I'll probably ask you to derive the complex rotation about any arbitrary axis. Make sense? Questions? Okay, let's see one numerical example. One numerical example from the book.
Can you define the question one more time?
Question?
Yeah.
The question is, okay, so I want you to, let's see from original. You do the modeling of the door, give all the dimensions, all the sizes, right? That's a good. So the geometry is taken here. Now I say, well, now you define a model of door. So the geometry, so you define door, right? And what's your geometry? So the geometry, the model you do. And then I say here, go simulate the transformation to open the door. Open door. And this is, will give you the transformation point. You define all the necessary transformation to open the door. Yes.
Okay.
And it has different parts. You could say there's no hint, no door handle. You just streamline. But you can start thinking about just simple cases and work on the complex. And now say, okay, so if originally there was something hanging on the door, after you open the door, where is that thing? Where's the location of that? Assuming this is something hanging there, or the label, whatever. So this is the point that's, after you open the door, this will be somewhere else here. So where's the final position of the object?
So are we required to apply it in WGL or just in paper?
Paper.
In paper, just come up with some coordination for the vertices, then.
Right, you do the modeling, right? You do the modeling, you define the transformation needed, and then give me a position. That means you apply a point and then apply the transformation to give you. Right? So here's the same thing, right? Find the P, the point, the model, the point, and then find the T, right? And then give me the final position, the new point, P prime. And this is on paper, right? Just to show me you understand what you're doing. Yes?
So we don't have to write all the program here.
no programming on the test, yeah, if you want to program it, I'll say, well, take home and do the program. Now, this will be on the project, on the exercise, you already done that, right? Yes. But I would ask you, if you were to program, what are the things that you have to do? Because there's a WebGL implementation or things, right? You have to, well, currently this part is probably easier, but later on when we do the 3D viewing part, setting up that, then you have different ways to do that for the program. So I can ask you later on, but for this problem, but this test, I'm worried, I'm just verifying whether you understand this part or not. This is the part that's we're trying to figure out. Make sense? And the most complex transformation we just said is rotation around any arbitrary axis, which means that I need to know whether you can understand the rotation axis, and after you know how to do rotation around that axis. But if that axis is not, it's given, I'm going to give you another reference point, so you know exactly, you only know about the rotation around the reference point, not this arbitrary axis that you're rotating about. We can simplify it to be something, to look simple, but the concept